This is the last lecture from chapter 15, all about acids and bases, and this is just kind of a couple topics that get pushed off to the end of the chapter, and one of them is dealing with how do we find the pH from a polyprotic acid, one that has more than one acidic hydrogen. And then also, how is it that ions can sometimes act as an acid or make a solution acidic or basic? Since polyprotic acids have more than one acidic hydrogen, the ionization happens in sequential steps. So, for example, looking at phosphoric acid, which has 3 acidic hydrogens. The first ionization gives us H2PO4 minus, and there is a separate Ka equilibrium constant for it. And then taking off the second acidic hydrogen, which, as you can imagine, is more difficult to do, right? The conjugate base of phosphoric acid has a negative charge, and so it's going to be a bit more resistant to giving up yet another acidic hydrogen to take on a negative 2 charge. And that is verified by the fact that the equilibrium constant for that second ionization is 5 orders of magnitude smaller. Okay, so it's 5 orders of magnitude less likely to occur. And then, of course, since there's a third acidic hydrogen, there is a third ionization, which again is several orders of magnitude smaller than even the second ionization. So how do we calculate pH for substances that are polyprotic? Well, lucky for us, most of the time there is a large enough difference between the first ionization equilibrium constant and subsequent ones that we can ignore the later ones. And the rule of thumb is if there's at least a difference of 10 to the third or 1,000 between the first ionization and the second, for example, it's pretty safe. It's usually safe to ignore the second one. It won't contribute significantly to making the solution more acidic. There are some acids, however, where the first ionization and the second one are closer. They're within 1,000, in which case you have to do 2 ice tables. The first ice table for the first ionization and another ice table for the second one. So for phosphoric acid, which we just looked at, the difference in the first ionization equilibrium constant and the second one is 5 orders of magnitude, right? So it is safe to ignore this second dissociation and make the assumption that it is not going to contribute to pH in a significant way. And just to kind of show you, if we were to go ahead and fill out an ice table for the first ionization, okay, and of course, since Ka1 is, it's kind of on the border whether or not you can ignore X, you could go back into the 5% rule and find out that it's okay, primarily because this initial concentration is quite high. But anyway, it's safe to ignore X, and then we get the X, or concentration of hydrogen ion, hydronium ion, whichever one you're more comfortable with. We can find that, and then we can find pH from there. Let's go ahead and do a separate ice table. Let's say that we didn't know for sure if we could ignore the contribution of the second ionization for phosphoric acid. And we want to know if the hydrogen formed from that contributes to pH at all. So we go through another ice table, and I just want you to see how the second ice table is set up. So first of all, the reaction we're looking at now is removing a second hydrogen ion from the initial conjugate base. Okay, so make sure that you understand this equation, how to write the second ionization of this acid. And then we're going to use the concentration of hydrogen ion that we found at equilibrium in the first step for our initial concentration, right? For both the hydronium ion and the original conjugate base, right? They were both X in the previous ice table. And then we'll use Y for the change in this one. Now again, Y is very, well, Ka2 is very small, so we're going to go ahead and assume that we can neglect Y. And there we would then solve that Y is 6.3 times 10 to the minus 8. And that is trivial compared to the concentration. So the concentration of hydronium ion from the first ionization is 0.19 molar, right? We got that up here. The concentration hydronium ion from the second ionization is, I'll put out in long form, right? So it's completely negligible. So we could have totally ignored this second ionization for phosphoric acid and it wouldn't have made any difference in the pH. All right, so there are some acids where the difference in the first and second ionization energy are close enough that you cannot ignore the second one. Sulfuric acid is one of them. That is one of our 6 strong acids. And you'll see a lot of times that it's shown that when you put sulfuric acid in water, people will often totally split it up, like step 1 and step 2 of the ionizations are strong, which isn't entirely accurate. So let me walk through a sample problem to show you how it'd be worked. This would be probably another good extra credit on your next exam. All right, so here are the first and second ionization energies for sulfuric acid. Here are the K values. Now we know the first ionization energy, H2SO4, for loss of its first acidic hydrogen is large, which means Ka is huge. So in other words, there's no equilibrium for this first step. So the concentration of any strong acid of hydronium ion simply equals the original concentration of the acid, okay? And so that was 0.75 molar. And so there's the contribution from ionization 1. Now, ionization 2, it has a smaller Ka, and that Ka, well, we know it's at least 100 times smaller, probably more, but we're not quite sure whether or not we can ignore the second ionization. So we're going to go ahead and set up an ice table. So let me erase some of this to get rid of the distractions. All right. So here is the chemical equation for the second ionization of sulfuric acid. And so here is the ice table. And again, the initial concentration of both the hydronium ion and the original conjugate base of sulfuric acid are simply going to be the concentration that resulted from the first ionization. And then we'll use X for our change. It's all a 1:1:1 mole ratio. Go ahead and set up our equilibrium expression for the second ionization energy. Now, in this case, it is not okay to neglect X, okay, because the Ka, that's pretty large, 10 to the minus 2. But lucky for us, look at how this simplifies. Since the concentration of the hydronium ion and the conjugate base of the original sulfuric acid have the same equilibrium concentration because of stoichiometry, look at that. They cancel out very neatly. And X, which is the concentration of hydronium ion from the second ionization, equals 0.011. And so we can see here that that second ionization does in fact have a measurable, although small, effect on the overall concentration of hydronium ion in solution. See, it would have been, if all we would have looked at is the first ionization, we would have gotten 0.75 molar for the concentration of hydronium. By taking the second ionization into account, it went up to 0.76. So, it's probably okay to neglect it, but it depends how precise you're wanting to be. So the rest of this lecture is on how on earth does an ion cause an aqueous solution to be acidic or basic. So you will usually see this in textbooks mentioned as salts can cause an aqueous solution to be acidic or basic. So just a reminder that salt is kind of a nickname for an ionic compound. And remember, ionic compounds made up of metals and nonmetals in general. So any soluble salt, any salt that is soluble in water, will immediately dissociate or ionize into the individual cation and anion in water. So we would write, for example, if we put sodium chloride in water, it would exist as the hydrated ions. All right, so you have a hydrated cation and anion, and it turns out that some cations and some anions can change the pH of the aqueous solution. I'm going to give you a summary of the rules first, and then I'm going to explain them to you. It turns out that if an ion is derived from either a strong acid or a strong base, the key word being strong. So again, you have to have the strong acids and bases memorized, okay? So remember strong acids, okay. So if an ion comes from a strong acid, okay, so that would be chloride, bromide, iodide, sulfate, should be perchlorate, or nitrate. That means that that ion does not have the capability of changing the pH. Now for ions that come from strong bases, so let's remind ourselves what the strong bases are. They are all the group 1 metal hydroxides, and the heavy group 2 hydroxides. Calcium hydroxide is debatable. What about strontium? All right, so if you have an ion that comes from a strong base, so the ones I've written here, lithium, sodium, potassium, rubidium, barium, strontium, they also will not change the pH of an aqueous solution. They won't have an effect on it. However, if there are ions from any weak acid or any weak base, which are most of the acids and bases, that ion will have an effect on the pH of the solution. So HF is an example of a weak acid. That means the ion from it, or the conjugate base from it, which is the fluoride ion, has an effect on the pH of a solution. So let's look at anions and cations a little bit more in depth and understand how they change the pH. So let's look at fluoride ion, which we know comes from a weak acid, hydrogen fluoride. So if we just take the rule at its word on the previous slide, we're going to say, okay, that fluoride is capable of changing the pH. Let's see how that happens. Well, if you put fluoride ion in water, you're going to get an equilibrium. Some of the weak acid that fluoride comes from originally is going to be reformed. But what's the byproduct? More importantly than this, what is the byproduct? When fluoride snatches a hydrogen ion from a water molecule, what's left over? Let me draw the water molecule out. So fluoride's going to snatch this, and what's pushed out, what's left over, is a hydroxide. A hydroxide present in aqueous solution is what makes a solution basic. right? Just like what makes an aqueous solution acidic is hydronium ion. So the fluoride ion is literally producing a certain amount of hydroxide and raising the pH. I should have even included that. So just to give you an example, if we made a 1 molar solution of sodium fluoride, the pH would be 8.5. And that would be exclusively from the fluoride ion reacting with water to produce one of the products being hydroxide. So let's look now at what a cation can do. We just saw that anions, if they're from a weak acid, are capable of making the solution basic. It's going to take some review on your part because there are a lot of acids and bases and weak and strong in there. Okay, so conceptually it's a little bit of a challenge. So let's look at a cation. Now, if cations are going to change the pH, they're going to make it acidic. Just like if anions are going to change the pH, they're going to make the solution basic. So let's look at a cation. Let's look at aluminum, okay? So aluminum comes from, just smush whatever, if it's a metal, smush it together with hydroxide, and that's the original base it came from. This is not one of the strong bases though, right? So that's a weak base. It's got hydroxide that it can release, but it's a weak base. So it should change the pH. Let's see how it does that. Well, these ions always, the mechanism of changing the pH is always to interact with water to produce either hydronium or hydroxide. So let's see how aluminum does that. So again, if I draw out a water molecule, and this is oversimplifying this reaction, but it gets the concept across. So the aluminum cation is going to be attracted to the oxygen, right, which is electron rich. And so it's going to snatch the opposite portion of a water molecule to make aluminum hydroxide, and the hydrogen ion is going to be left alone, which of course it's going to find a water molecule to jump on. But so the bottom line is cations, if they're from a weak base, will react with water to produce hydronium ion and decrease the pH. So cations will tend to make acidic solution, anions will tend to make basic solutions. And just kind of confirming that, if you have a 1 molar solution of aluminum chloride, pH of 2 to 3, and that's from the aluminum ion interacting with water to make hydronium ions. So let's just kind of go through the concept again, because I know it can get confusing for students. So we learned in the first slide on this topic, that only ions that are from weak acids and weak bases can change pH. So let's look at a bunch of acids and bases and remind ourselves what some of the weak ones are. So the strong acids are at the top of this particular chart. So every other acid below those strong acids are weak acids. And so the ions from any of these weak acids can and will make an aqueous solution basic, okay, by interacting with water. So you just kind of look at the ions that all of these can make. SO4, phosphate, fluoride, nitrous, acetate. So any of the ions or conjugate bases you can think of for any of these weak acids will change the pH of a solution. And this is how they do it. Just kind of, I'm just trying to kind of solidify this new information in your head. So it may sound a little redundant. It is. So if you take, again, all of these conjugate bases from weak acids and you interact them with water, they're all going to snatch a hydrogen ion from water, leaving behind hydroxide. And again, that is how all of these anions will produce a pH greater than 7 or basic in solution. let's look at cations a little bit more in depth and kind of just emphasize the mechanism for them too. So what are some cations you might run into that are from weak bases? Most of them that you're going to see are actually going to be metal, okay? So any hydroxide that is not a group 1 or most of group 2 hydroxides will be weak. Okay, so these are hydroxides. The metal is not from group 1 or 2. And so these would be weak bases, and the cations from them would be capable and in fact could and would turn the pH of an aqueous solution acidic. Now another one that you're going to run into, hopefully you remember me saying that nitrogen containing compounds that are neutral serve as a weak base. And so you are also going to encounter the conjugate acid, that should say weak base. You're also going to come across the conjugate acid from nitrogen containing weak bases. Okay, NH4 being one of them. Now NH4 is acidic because, as you can imagine, if you combine NH4 with water, it's going to donate its acidic hydrogen ion to water, producing hydronium ion and leaving behind the neutral weak base ammonia. So if it's a metal cation you're talking about, again, metals are they're electron deficient, especially as a cation, right? And so they are going to interact with the electron-rich oxygen in water and kind of cleaving off the hydroxide, kicking out the hydrogen ion, which is increasing acidity. Now we're going to ramp it up in complexity. So we don't have the luxury of going into the chemical storeroom and pulling out an anion by itself or a cation by itself. The source of cations and anions are going to be salts, thus the name. So NaCl would be in a jar that we would pull down, and we would get both the cation and the anion. We can't selectively have one or the other because all substances in our world are neutral overall, so every cation has an anion next to it and vice versa. So it's likely that you're going to be given an entire salt, such as sodium chloride, and asked, is this salt as a whole capable of changing the pH? And if so, which way? And what that's going to require you to do is look at both the cation portion of the salt and the anion, and then determine if each one individually will change the pH. So remember that if cations are going to change it, they are going to make it acidic. And if anions are going to change pH, they will make it basic. I'm going to walk you through the thought process you need to do if you're dealing with an entire ionic compound or salt. So you would first separate the salt into its individual cation and anion, and then each one of them present a separate problem. So let's look at the sodium cation first. So you have to determine what base sodium cation is from. So remember I said if it's a metal cation, just stick OH to it, and that will be the strong base or the base that it's from. And then you have to memorize the strong acids and bases. So hopefully you would know sodium hydroxide is a strong base, which means that the sodium cation came from, that's the strong base it came from, and we have been taught that ions that come from strong acids or bases are not capable of changing the pH. Okay, so I'm going to show you why. All right, you can memorize that they're not capable of changing pH, but I want you to understand why. So if a cation were to change a pH, it would be by reacting with water. And I've shown you a couple examples of those. The positively charged metal would be attracted to the electron-rich oxygen in a water molecule. snatching a hydroxide and kicking out the hydrogen ion, right? So, but it turns out that if this sodium cation were to snatch a hydroxide and couple up with it, you get sodium hydroxide. You're regenerating this strong, or the acid or base it's coming from. But this is strong. What's the definition of a strong acid or base? The definition of a strong acid base is they don't exist intact in water, okay? So this will never be formed. If what it comes from is a strong acid or strong base, it will never be formed. Or the instant it's formed, it's going to break back apart, right? And so that's why it can't change a pH, because it can't go back to its original strong acid or base. Now, same thing for chloride. For the anions, okay, they come from an acid. So the anions you're typically just going to be adding a hydrogen to find out what acid they came from. Okay, and as in the case of sodium, the acid chloride comes from is HCl, which we know is a strong acid. And again, the very definition of a strong acid is that it does not exist in the intact form in water. So HCl would never be formed, or if it was, it would immediately separate out again to the individual ions because it's just not stable in the intact form. So again, cations and anions that come from strong acids or strong bases, you can ignore. They are going to have no effect on pH. I created a list of the steps that you will undergo if you are to determine if an ionic compound is going to make a solution acidic or basic. And the first thing you want to do is go ahead and dissociate or ionize the ionic compound into the individual cation and anion. So let's say that I did barium nitrite. It'd be nice and challenging. Okay, let's say that I gave you that salt and said, if I dump that in water, is the water going to be neutral, acidic, or basic, and why? So the first thing you want to do is separate that into the individual cation and anions. Okay, so step 2, you got to determine separately whether each ion comes from a strong acid or base or a weak acid or base. So with the cations, you're going to smush them together with hydroxide if it's a metal. And for the anions, you're going to just add a hydrogen ion to them to see where they came from. Then you are going to evaluate whether the substance you determine these ions came from are strong or weak acids and bases. It's just memorization again. Barium hydroxide is a strong base. It's one of the 6 strong you were supposed to memorize, which means that barium will have no effect on pH. The nitrite, notice I didn't use nitrate, which would have been strong. The nitrite comes from nitrous acid, which is a weak acid, which means the nitrite ion will have an effect on pH. So let's look at what that nitrite will do. It's going to snatch one of the acidic hydrogen from water to reform nitrous acid, and then what's going to be left over is additional hydroxide. So the barium nitrate is going to make the solution turn somewhat basic, exclusively due to the nitrite ion. And that is it for this lecture, and it's also it for Chapter 15, Acids and Bases.